Hello and welcome to episode 230 of Quarkus Insights. So we're going to be talking about hypercharging Java with Leyden, and we've got Maria as a special guest. So welcome, Maria. And I guess before we jump into to hearing more about this, which I'm definitely looking forward to, we've got a little bit of news. So I get to push the news button. Although our news is actually non-news, which is that this is our last Quarkus Insights of the year. So we'll be back in the new year because people are taking holiday. And for similar reasons, we will be continuing to do the cadence of micro releases for Quarkus, but we don't have a minor release this month. Both because the people doing the release will be on holiday, but also because it would be a very boring release because the rest of the team are on holiday. So normal service resumes in the new year. But with that out of the way, let's jump right into it. So to start, Maria, maybe you can give a bit of an introduction of sort of who you are and what your background is and what your involvement with Quarkus is, because I know you've done a whole bunch of different things with Quarkus, which is amazing.
Yes. So, I'm Maria. I have been working with Java for a very long time. I was on the middleware. Well, I'm still on the middleware team of Red Hat, but that was moved to IBM. Thanks. But there, I work with Camel. I work with previously to that, I was focusing more on the synthesis, which is a user interface that we had in Red Hat for Camel for integrations. And then we moved to Gauto, which is a project I created with Rachel and Zineb. And then it's the same thing, but a new interface for Camel. And then at some point, I was moved to the OpenJDK team inside Red Hat, still Red Hat IBM. And there I moved on to much more complex stuff because the OpenJDK source code is beyond anything. I mean, it's impossible to to have everything controlled. The first, I have been there for 2 years already. Well, with a maternity leave in between, but yeah, for 2 years.
Yeah.
And
Yeah, 'cause I thought it was like last week that you moved, but time just flies.
time flies. That's been already 2 years, and I moved there and I started doing backports, doing basic stuff, trying to fix something there. And then I was moved to the Leyden team, and I feel more like a fly on the wall on these conversations because they are developers that have been with the OpenJDK source code for decades sometimes. And but I'm there, and I was assigned this task of creating a diagnostics tool. So when people use Leyden, can understand better what is happening on their application and can get more power from Leyden than if you are just blindly trying to apply it. So that's what I'm doing.
Yeah, well, yeah, that sort of answers two questions actually, because one of the first things I did in my career by complete coincidence was I was in well, not OpenJDK, because OpenJDK didn't really exist at the time, but I was in the J9 team, and so it was similarly sort of very low level. And the thing that I ended up doing there was making diagnostic tools. So slightly different, but yeah, sort of similar thing, looking at
Yeah, but
diagnostic
because
tools for.
it makes it easier. I mean, I have been learning a lot on how Java works on the inside, and it's amazing. But in the meantime, while I learn, it's useful if I do like lateral stuff that help me understand and help other developers do whatever they're trying to do to interact with Java.
I mean, I think it sort of shows the benefit of having someone new join a team as well, actually, because you might think, oh, well, the people who are new can't bring anything because they don't know everything. But that's exactly why they bring so much, because the people who've been doing it for 20 years, they just sort of read the assembler and know what's going on, and it's obvious to them. And everybody else is like, well, wait a minute, how do I figure out what's going on? Can we make this easier? Because this is hard. And that's the sort of the huge value.
Yeah, and also every time I ask, okay, where is some documentation I can read to understand what is happening? What documentation? Just read the code. Yes,
Yeah.
but on which file do I start? Where do I start
Yeah.
reading the code? This is not as easy as it seems. So yes,
Yes.
having
Yeah. Or
someone
the
starting is oof,
yeah. Yeah, because it's either just read the code or just ask so and so, which is not a scalable approach.
not at all. Every time I try to ask, okay, now we are doing things with the compilation. So where is it defined exactly? What does the compiler inside the OpenJDK does? How does it convert to bytecode to native code? Just check the code. Okay, but no, that's not the answer. At least give me a hint on where to start reading the code because the code is too big. It's impossible. Yeah.
Yeah. Although I guess that's sort of the argument against documentation is I've also done quite a lot of effort, sort of, where you write the documentation, you're like, great. And then the code changes and then the documentation is stale. And it's like, oh, actually, now the documentation is worse than not having documentation. But that's a whole different topic.
Yes, I have where is it? Here. I have no I'm making a lots of notes and diagrams and things. And at some point I thought, okay, this is getting big. Maybe I can write a book with this. But no, because when the moment I have this book written, it's going to be legacy code. It's not going to be current code. It's not going to be useful. So no, it's weird, but it's very very fascinating also.
Yeah. Yeah. So shall we talk about Leyden?
Yes. So if you put up the slides, so I made some slides. It's very difficult to make. I'm going to start explaining what Leyden is because I know we have discussed this on another Quarkus Insight with Andrew several times, I think. But just in case someone is here and doesn't know yet what Leyden is, but it's very difficult to put it in graphics. So I don't know if this is going to, if this approach is going to be fine with you. So the first thing I want to talk about is the difference between compile native code and when you run something with the jar file. This is okay, like this. Because a few years ago, before I joined the OpenJDK team, when I started any kind of project, I usually make sure that it was going to be Quarkus and native compilation because it's good, it's really fast, it makes sense. And what it does is you have your Java code, you compile it to native code, machine code, and then you run it, and it's faster than running a jar file. But it's true that the same code runs from the beginning to the end of your run of the application. It's not learning, it's not improving as you use it. So that's some main difference with the jar files. On the jar files, when you start, well, this is not going as smooth as I thought. So when you start a jar file, it starts very cold. You have bytecode that is inside a jar file, which is a zip file. It's very easy to check what is inside. And then the Java virtual machine starts reading it. It generates some metadata based on the classes that it's loading. That metadata also contains information on the methods. It loads a lot of stuff from the bytecode and then tries to translate the bytecode to machine code. And what it does, the first few runs of each method is for each bytecode in Java, I have a table that translates this 4 or 5 native code machine assembly code. So you just check the bytecode, run this, check the next bytecode, run the following, check the next bytecode, run the following. After the warmup, the Java virtual machine knows that this is not a very efficient way. It's a very efficient way of running code compared to what interpreted languages did 30 years ago, but it's not very efficient compared to native code. So it starts profiling the methods. When you run a method for the first time, it creates a method counter and says, okay, this was run one time. If it runs another time, this was run 2 times, 3 times, 100 times, 1,000 times. And it also gathers statistics on how the code is running. It's not only how many times, but how it's running. If it, for example, if you have different branches of code, like a switch code, if else, it starts checking statistics on how many times do I enter the first if else, the second, the third, the fourth branch. And it starts getting these statistics so it can compile later based on those statistics. It's not. It starts compiling the bytecode to native code based on those statistics. So it knows, for example, if you always enter an if else, you 90% of the times you enter the else. Maybe you can start doing some of the code inside the else before, because our CPUs are very parallelized right now. You can do several things at the same time. So while you're running the code before the if else, and before checking and knowing which branch you are going to enter, you can start doing what is inside those branches. And if you 90% of the time knows that you go to the same branch, you can start running that branch. 90% of the time, when you reach that code, this is already done. So you are faster. 10% of the time, you missed. Okay, I'm going to have to drop these instructions that I started, but no harm done because the CPU is prepared to do that. So it starts doing this kind of optimizations, this kind of compilations that takes into account what has been happening and how your application interacts with whatever, if it's getting requests, if it's getting user input or whatever it is. The thing is that this is a kind of these statistics are very difficult to get on build time. You need to be on runtime to get those information, because on build time, for example, what Quarkus does. If this class is not used, I'm just going to remove it from the class path. If this method is never accessed, I'm just going to remove it, and that accelerates the startup. That makes the footprint of memory smaller, but you don't really know how your application is going to behave. So this is something that Java, the OpenJDK, does very good, but it has to be done with the bytecode. Also, it knows exactly your hardware and it knows exactly the version of the CPU that you're using, and it knows exactly, for example, how much memory you're using. And that also helps in the compilation, because instead of using the generic set of instructions for an x86 or AMD 64 or whatever, what you do is use the set of instructions specific for that CPU. So it's even faster or has some specifics that make it more efficient to run it some way or some other way. And that's something that you also cannot do on build time. You need it to be on runtime to know exactly what is the CPU you're doing. So after some time, and it depends on your application, it can be nanoseconds, it can be milliseconds, it can be seconds, or if you have a server that is lazy and has only one request every hour, maybe it can take hours. But at some point, if you use your application enough, you have a peak performance that is better than anything you can have on static build native code, because you have all this information. You have exactly what hardware you're using, you have exactly what your users are doing, you know exactly how your application behaves. So in the end, you have a slower startup, but then you get hotter and you get a more optimized code than if you just run native code. And with this in mind, this is what people in the OpenJDK team, the people that the architects of Java, they thought, well, what if we could start at the end of the warmup? What if we could somehow get all this information at the beginning, and instead of starting cold, we can start already hot And we can start already with all this information of we are going to use this hardware, we are going to use this specific set of instructions. We already have compiled code specifically for your CPU and your use case. What if we could do that? And that's what Leyden tries to do, tries to get all this hot at the end or at the middle of the run and try to move it to the beginning.
I really like your visualization, by the way. I haven't seen that before, and it makes a lot of sense with the
Yes, it
the hot and the
makes,
cold. Yeah.
this is a lot of drawing here.
Yeah.
Oh, so you're kind of like Holly. You draw everything by hand.
I could do that, but no, I don't. I don't draw very good at hand. So this is the idea. You have the jar file. You have build time information, the bytecode, basically. You do kind of a training run in which you get the startup, warmup, peak performance. You get the hot runtime information, and then you generate an AOT cache. An AOT cache, which all the runtime information, profiling, metadata, heap data, native code, whatever. And then when you run the production run using the same jar file, you inject also the cache, and then it's hot directly. That's the theory. In practice, we are still not 100% there. For example, adding native code is something that is still on testing phase. It's not going to be on JDK 26. We hope it's going to be on JDK 27, but maybe if we find issues, it's going to be JDK 28. We prefer to do things slower and not break things instead of trying to be fast. There's always something in each JDK version about Leyden that is moving forward. So the idea is that with this, startup and warm-up time and peak performance reaches are faster.
It looks almost like Leyden is borrowing a lot from the design ideas of Quarkus itself, because that's kind of the thought process we went through like before Leyden was even announced.
I mean, it's very similar, and all the pre-processing on the build of Quarkus and removing stuff and changing stuff, it's very similar. But the truth is, you need runtime information to be able to do this properly. And there's a lot of things here that Quarkus cannot touch because it's inside the OpenJDK. For example, this is something that has been, parts of this are something that have been there for a long, long time. The CDS, the class
Data sharing. Yeah.
Because at the beginning of all runs, there's a lot of things that are common and always happen. Like you're going to read the bytecode of Java lang object, Java util string. There's a lot of classes that are going to be converted to metadata, stored into memory, and they're always the same for all applications. And then for your specific applications, there's also another piece of code that always runs that is always the same. I'm going to start my application always with this class, and then I have to convert it to I have to add the metadata to the memory. I have to create this. I have to create this. So there's a lot of things that always happen. Always, it's deterministic. It always happens the same way. It always happens in the same order. And before CDS, we did it manually. Then with CDS, almost all, at least OpenJDK, I can talk about other Java JVM implementations, but at least on OpenJDK, you always have this CDS that already preloads things that we know are always going to be there. And it depends on the JDK version, of course, because there are things that are different on each JDK version, but part of this was already there with the CDS, and what we are doing is expanding that and making it a bit more specific to the applications.
I sometimes talk about it as the goldfish problem, that like it's just redoing the same, all this work every single time it starts. And if you start 100 times, it redoes all that work 100 times, which is just silly.
Yes. And part of why I think it's important that this is done on the OpenJDK side is because there's a lot of frameworks trying to do this kind of stuff, but each doing it on their own way. And maybe it makes sense that the frameworks experiment on how to do this. But in the end, if we are all doing the same things, just move it to the OpenJDK and leave the frameworks focus on the things that really matter, I think, or the things that are different.
Yeah, that's like the whole open source model in general. Like you get these specialized things that do stuff, and then everybody else learns from it and figures out that we're all doing the same thing. And it's like, okay, why don't we benefit everybody and do it in a standard way?
Exactly. And the things that you can do if you're doing OpenJDK code is you get further than if you are trying to do this with framework Java dependencies libraries. So how to do this? There's two ways. One is in 3 steps. First, doing the training run, recording all this information, then doing an assembly run and creating the cache, and then production run using the cache. Or you just do as below, 2 steps. Execute training and assembly in 1 step, which is probably what most of the people will want, because why separate an assembly run in which you just run the assembly run and wait, and then that generates the cache output, and then you execute it. And there are some constraints here, and once I explain why there are constraints, you will understand it makes sense. I mean, you cannot do it any other way. So you need the same hardware, both in the training run, where you get all the information, and the production run, when you really run this thing. Because if you are getting all the optimizations based on the specific chip, CPU version, blah, 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 you need to use the same hardware. If you create statistics based on a different CPU version or different chip, then all those statistics cannot be used on your production chip. So you need to use the same hardware with the same configuration, like same memory size and same disk access, same everything as close as possible, the hardware on production and training. So all the optimizations and all the statistics make sense, because if you change it, then the statistics are useless. And the same happens with the Java version and the source code. If you change the Java version, it will change the OpenJDK source code, or if you change your source code. So if you are loading, if you are caching, okay, this class has these fields and these methods, and then you change that class, then what you have cached is useless. Or even worse, you try to run something that doesn't exist anymore. So you need to have the same Java version, the same source code, the same hardware. The JVM options, there are many that you can change. For example, you can use a different garbage collector. That's something that is, you couldn't do it in JDK 25, but you could do it in JDK 26 now, I think. So garbage collector is something that you can change, but do you want to change it? That's the question. Because if you change, different garbage collectors store things differently in memory. As you know, they handle things differently. So if you train your application and get the statistics based on one garbage collector, and then you use a different one, it's not going to break, but maybe your statistics make less sense. So, and anyway, why would you want to train in a different environment than what you're going to do? The production run, to me, it doesn't make sense. Maybe there is some reason to do that. The operating system also, it has to be the same, because the source code of the OpenJDK is different depending on the operating system. For example, how you access files on the disk is completely different. So if you change the operating system and you have cached some classes, some things that are specific to the operating system, if you change it, then you will have something cached that no longer exists, or you will have, in the best case scenario, you have to throw that cache to the garbage and start again. That's the best case scenario. The worst case scenario is you're trying to access code that doesn't exist. So you shouldn't do that. And that also leads us to the custom class loaders, which I think is a problem with most frameworks, because that's...
Quarkus has definitely been scratching their head over that one.
So this is I would say this is this is optional. It's not going to break your application if you use something with custom class loaders. It's simply that Leyden will ignore classes loaded with custom class loaders, because right now what we are doing is we have things on the cache and we kind of trust them, not blindly, but we trust what is on the cache, that you load it into memory. So the moment you start adding things that have been loaded by a custom class load, maybe there's some malicious code that can get inside, blah, blah, blah. So it's not that we are not going to support that, it's that we don't support that yet. Just because there's a lot of implications on trusting class loaders blindly or almost blindly that we don't want to enter that yet. It's it's going to be it's going to be supported because there's it's something that is being used, but probably not in the short term. But it doesn't matter because we still have we can get a lot of the power from Leyden even if we use a custom class loader. So this is the fruit testing application that we use for Quarkus benchmarking, and this is a machine that so as I say there, this testing focus on the trend, not the numbers, because this was not a container in the cloud, blah blah blah, that you can make sure that everything is fine. This was just a machine that we made sure no one else was doing anything at the same time. We tried to make the testing more or less reliable, but this is just as if you run it on your machine. And you can see that I'm using the Quarkus superjar there. I'm comparing the normal Quarkus with Quarkus superjar just because the Quarkus superjar is not using custom class loaders, to compare and see that it gets an even bigger difference when you use Leyden. But this is Quarkus superjar is not the way to go to production, so don't use it. It's just to compare what happens when you don't have a custom class loader. And as you can see, the first thing we get is the time to opening the port, and it already is faster using Leyden. This is just because normal Quarkus have to do a lot of loading, metadata loading, blah, 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 parsing bytecode. And with AOT cache, we have a lot of that already prepared. So it goes directly to memory. And these two graphs are mostly the same because once Quarkus start, the time to get responses from the request is so fast compared to the time it takes to start, that it doesn't make much sense to. But yeah, I wanted to show that, yes, I mean, it's there, it's fast. And if you can see, this is how much time does each request take. And this we ran this test several times, and it always the Quarkus with Leyden is a bit faster. There's not much difference, but there is some difference there. And you can see this trend until you reach peak time, all the warmup. And it's very interesting to see that both the Leyden and not Leyden both have a similar curve. And the only difference is that as the AOT cache already has some things already there loaded into memory, it is just a bit faster reaching peak performance. But it's very, very nice to see that even when it takes some time, takes like 5,000 requests, it gets to a point where response time is negligible. It's just instantaneous. The only difference is that as Leyden prepares things before, it's faster reaching that peak time. And
what's going on with the? Oh, sorry.
No. Ask me.
With the in the first chart when it's so sort of ziggity zaggity and then it goes flat, what happens at that transition?
That's probably compiling things.
Right.
Because we don't store compile code yet. This is
Got it.
before that. We did some testing with compile code and it's even faster, but the difference was not big and the code is not yet ready. So we prefer to show. This is with JDK 26 latest, whatever was on the source code when we ran this a couple of weeks ago. And yes, the idea is that at the beginning it starts compiling things, then stops compiling, then starts optimizing for whatever it's doing, blah, 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 until it's so fast. It's incredible. Then the overjar is very interesting because it starts, if you compare the left graph, the overjar is the one without custom class loaders, so it doesn't ignore the things that were loaded with class loaders. So there's more things loaded from the AOT cache. And you can see that it's even faster at the beginning. And then around 2000 requests, it has a bump. And we are still investigating why that bump is there. We think this is because at some point, the normal run de-optimize a bit to optimize again.
Right.
This makes sense because at some point it has to check if the behavior of the user changed for some reason. Maybe it's Black Friday and suddenly people are doing a different stuff. So every now and then it de-optimize, check again the statistics, and optimize again. So that's this happens on all applications, but on our case, it happens sooner, because as we have the training before, it's not only 2000 requests, it's 2000 plus all the requests that were done on the training run. But it's much faster at the beginning. The valley at the start, and even then with that hump, well, this is ridiculous because after 5000 requests, the response time accumulated is so fast you don't even notice. Here we have the hump and there is some upwards response time, but still. But even with the hump on the overjar, the compilation to recompile again, you notice that the startup time is very hard to catch up later. And this is average response time, just to show that at the beginning there's a lot of difference. There's some difference between the Leyden version and the non-Leyden version. But at some point, well, after 5,000 requests, the numbers don't exist because it's so small. But you can see that after reaching peak performance, the difference between Leyden and not Leyden is negligible, because you cannot distinguish, because both have reached peak performance, and everything that were helping the AOT cache to be faster at the beginning, it's diluted completely.
And I guess that's quite different from what you would get with native, where you'd get much more benefit at the beginning, but then as time went on, it would become
Exactly.
Sorry, I've just completely lost the ability to words, but you know what I'm trying to say.
Yes, native will be always a constant. It will be faster at the beginning, but it will be a constant. So at some point, probably long before the 5,000, it will be much worse than running. We have to do that comparison too, because that's interesting. At what point does native gets overridden by this? Because this is so fast. I mean, the numbers here, sometimes there is this big, but this is just because it's so small, the numbers. Maybe I'm not even testing this properly, because the numbers are so small. It's very difficult to find if this is exactly what it took, or maybe it's just network connection being a bit slower, or it's just that my testing framework was not fast enough to get the answer. So
I think that's consistent too with what we tell our users, that in general, not just with Quarkus, but when you do native compilation, you're going to sacrifice overall throughput for long running applications.
yes, and it will be interesting. I think we have to come back at some point in a few months and do the comparison native, jar, Leyden, because I think it's going to be like that. At the beginning, the native compilation, of course, is faster, or not, because once we have JDK 27.8 that has compiled code on the AOT cache, that's like native compilation, but better, because it will be more optimized than the native compilation. But the main drawback here always is having a good training. Having a good training, being able to do training the proper way in the proper place, because how do you do the training without that interfering with your production systems? So you roll back a new version and you need to train that before you really do the production. So some people do that in canary deployments. I do a canary deployment with the training. If that goes good, I already have the training. If that doesn't go good, I just throw the training and the canary deployment. But then you need to have canary deployments. Maybe you don't have canary deployments. Or maybe you want a canary deployment that has some specific blah, blah, blah that is different from production, and then you cannot train it there because it's not exactly the same as the real deployment. So how do you do that? It's not straightforward. It's not that easy to do the training. But at least for the people that do canary deployments, it should be easier. But then, for example, if you just have a desktop application like IntelliJ IDEA, how do you deploy the cache? Are you going to give the cache to your users with this version of Java, this version of the hardware, this version of? We have been asked to have to be able to generate hardware agnostic, more or less, version of the cache. Like I just want it for this family of processors. But then you are losing part of the optimizations for your specific machine, or things like that. How do you are you going to just say, okay, then the first time you open this application, it generates a cache, and then that gets stored forever? But what if the first time you open the application, you just try a couple of buttons, say, okay, I like it, and then you close it? That's not proper training. That's not even real work that you're going to do with that application. So generating the cache is an issue, and so that's something that we need to work on, how to make it maybe less specific, or be able to be less specific, but then you lose things. Then how do you deliver how do you give the application with the cache, or not give the cache? Maybe generate the cache every n times you open the 10th time you open the application, then you generate a new cache. But then that's risky, because what if that time you don't train your application properly? So that's a problem.
Yeah, when I sort of first started hearing talks about Leyden, one of the sort of the visions I heard was this idea that you could have like this sliding scale. So at one end would be sort of how things were, and then at the other end would be native, and that you could sort of, depending how hard you want to try with your DevOps, you could sort of choose where on that scale you would be. But it gets hard to sort of choose the right point and reliably be able to position yourself.
Yeah, and also, for example, JBank, you can use different Java versions and minor versions, and every time you change it, you need a new cache. So, how do you do that? Are you going to store a different cache for each Java version? and plugin you get into, or some we are also discussing how to be able to maybe have a generic Quarkus cache that you can add to your application cache, that you somehow unify both. Can we do that without breaking things? It's weird. It's weird and it's not clear, but we are advancing. And this is, I think, this is the moment to open this kind of discussions, and people that are interested in having this kind of advantage in their applications, they should test it now, not in 5 years, because now we have developers working actively on this, and we are defining how the architecture is going to be, how this is going to work, what are the constraints. But if you test it in 5 years when this is finished and other people have already applied to this and are already using this, if you have some need or something weird that is happening in your application, maybe there won't be as many developers interested in checking what is happening there if it's already working for the mainstream public. So I think this is the moment to test this and say, okay, I like this, I don't like this, I have this weird hump in my graph and I want to know why, if it's something I'm doing, if it's something that Leyden is doing. And this is the moment to do that.
I think it's interesting too when you start talking about, especially like the multiple JVM versions. I'm not sure, like people who are building actual applications, how often they're testing against multiple JVM versions or multiple hardware specs. But framework authors like Quarkus and Spring and Micronaut and all those folks, I'm sure, are doing lots of multi-JVM version matrix testing and all that, and multi-hardware. So this is an interesting conversation when it comes down to the frameworks. And how do you build the cache, and how do you know which version you're going to baseline on and test against and actually do your benchmarks? I think it's an interesting conversation.
Yes, and it's not only interesting conversation, but I think it's interesting to have people with real applications using this and saying, this is not working for me, or this is working for me, or I need this to be more like this or more like this other. And this is the time and place to do this, because we are, for example, we are discussing the how to make the cache more generic, maybe with some argument, and being able to use family architecture instead of your specific CPU. But is that enough, or do we need something else that needs to be generic on this? Because we also discuss generic Java versions, like you can drag your cache, you can update your JDK and drag your cache forward, not backwards. We don't do that, but at least forward. But that's a lot of work around it, and a lot of optimizations you're going to lose, because the metadata is going to change, the code, maybe you will need to trash the code because it's not the same. Do we really need this? Or does it make sense to have a different cache for each JDK? So these are the kind of questions that are right now on air, and we need to answer them. What is inside the cache? This is something that changes on each JDK version. So I talk about the metadata. That's really important. So for each class that you have the bytecode on the class path, when it gets it gets used, when it gets loaded, which is not, maybe it's not directly used, but used by another class or used by another method. But when it gets loaded into the JVM, there is some metadata associated to it that gets created in memory that says, okay, this is this class, these fields, these methods. And then there is the constant pool that says, okay, I have this symbol, this class mentions some other class. Where is this other class? It's here. So it helps the linkage between classes. Then we also have inside the metadata box the method data and the method counters, which method counters is what stores how many times a method has been run, and the method data is the one that stores this profiling information on how the method has been run. And we also store now some instance classes, like Java instance from string classes. When you have a string hard-coded in your source code, which can be the hello world in the hello world system out println, or some error message or something that's a string hard-coded, that always gets loaded the same way on the OpenJDK when you run your application. So we can just say, okay, this Java instance string, yes, put it in the cache. We know exactly what is going to be, how it's going to look like on memory. So let's put it there and load it directly. And the Java instance class is the same. For each class you have defined on your application, your class path, there is a Java instance class. The class you get when you do a .get class method. That's an instance of a Java lang class that represents your class. So these kind of things are always loaded the same way, are always looking the same, and we can store it in the cache, and we do it. There's also the profile data, class training data, method training data, compliant training data. This is specific from Leyden, and this is it stores information on, for example, the compiled training data. That's very obvious. If this method has been compiled, at which level, at which with what characteristics, and it also, the class training data contains links to the method training data of the methods that that class contains. And then the code is something that is not yet there, but as I said, it's going to be soon. And the idea is to have stubs of code already compiled. So when you start the application, you already have the native code compiled. So it's faster. So this is what is inside the cache, more or less. The part that is static, that's always the same. That's you can even not dump the memory because the addresses change. So you cannot directly dump the objects, but you can say, okay, this is always the same, so it's just going to be a copy from the cache to the memory. And the dynamic part is the part that is more trained, that is runtime information. So the CDS is the CDS that we talked before, the class data sharing. That's part of the static that is always the same, but the CDS focus on OpenJDK classes, and on this now it doesn't always focus on the OpenJDK classes, but also on your application classes. And I have a demo. I don't know if you have any questions before. So this is the diagnostics tool I have been working on to be able to understand what is inside the cache. And this is the source code for the demo I'm going to do. Let's make sure that I'm not... Yes, I don't have anything weird here. So I have a very simple application. It's it even has tests. It has a couple of resources. This lists all the cats. This is for adopting a cat. Let's start it so you can see it how it. This is not broken. It should appear here. Not yet. Here. I can adopt a cat, shows me a photo, and I say, okay, I want to adopt this, or I don't want to adopt this. And if I adopt, they get added to the list of cats adopted. It's very simple, very basic. So let's see. I'm going to use the Uber jar to build it and to avoid custom class loaders, but
So that's an interesting use case. The cat adoptions. I actually have a whole application built around that I use for demo purposes. So you're welcome to it if you'd like it.
Yeah, the internet is for cats.
of course. So I'm going to clean because I store the AOT cache there. So on target, so I clean, I build, and yes, it's slow because my machine is slow. I just received a new one, but seriously, this is just a very trivial test. Okay. Building jar, which is the Uber jar. And I run it. So I'm going to run a training run. It has the AOT cache that is going to be stored on target app AOT. This is to write a log file that is going to be a map file of that AOT cache to know exactly what is inside. This is logs to know if there is something wrong with the AOT, when a class gets loaded, etc., and then load the jar file. Okay. So for training, I have this that runs 100 requests using URLs that are on a file. It worked. Success rate 100%. And now I stop the application. And it's going to take a bit longer to stop because now it's generating the AOT cache with what's on memory. Sometimes there are some errors there. You don't have to worry about that. It's just because sometimes for storing things on the AOT cache, as we are going to trust them later, it does some validation just in case something is fishy, then it gets the class out. We will explore that later. How much time do we have? Infinite?
Somewhere between 7 minutes and infinite. So in principle, we stop in 7 minutes, but we're pretty flexible.
No, it's not going to be that. If this goes a bit faster, it's not going to be that one. That more than 10 minutes. Okay. Cache created, and it's big. And now I'm going to run my tool.
And yeah, I guess the size of that cache is sort of showing the why you might not want to generate a cache for every JVM version and every hardware and bundle them up with your application because it would just explode.
Before checking the cache, I'm going to run a production run. So you see how it's done. So what it does, before we have AOT cache output, now we have the same without the output. I'm going to run some log files. It runs. Hey, I have a cat. Yes, blah, blah, blah. Of course, yes. So, diagnostics tool. I'm going to load the map file. I'm going to load the training logs. and the production log. We only have one training log, 2 training logs. That was fast. So this is still loading the AOT map file, but we can start already checking things like the info command. And it says that only 88% of the classes were cached. So on my production run, there were 12% of classes that were not cached and loaded. And that's weird. That's not good. So how do I get which classes were not loaded? I say, okay, I want to see classes that were loaded in production that were not cached. And I'm going to restrict that to my package because if not, I will get a lot of OpenJDK. So I get, there was a class that was loaded during production, but not during training run. This is weird because our training run should have loaded all the classes that we were going to use in production. So first things to check is that our training run, how was the training run, if it was good or not. And then you see that I'm calling the HTML files and the presentation mode instead of calling the endpoints. So that doesn't make sense. I have to call the endpoints. If I run this again, I should now get, instead of the index HTML, I should call the endpoints. So it should train better. Right now, I haven't done any training. The training was just starting the application and serving HTML static files. But that's probably not going to be enough. Why? Because if this was done properly, I'm going to skip some parts. I can see which classes use cat photo generator, and it says no classes are using cat photo generator. So I'm going to check, okay, maybe I have some class that was loaded. I'm skipping things here. Classes, kitcasts. On my package, I see there's a lot of things like beans, methods. I'm going to restrict by classes. There are beans that are generated by Quarkus. They have been added to the metadata. And it's fine, it's nice, it's working. But one thing that I haven't checked here is that this is not what we need to do. Is not the training run is not a testing run, it's a training run. So if I have a parameter that says test with default value true, that's not what we need to do. We need to change the query parameter test to false to make sure the training run is not a testing run. I don't know if I'm explaining myself right. So when I run this, I have to remove, let's remove logs and AOT and run again the training run with OHA. And I run the production run. Beep, 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 beep. Reading configuration. So it's a very simple application, but the cache is big because it has a lot of OpenJDK classes.
Yeah, and I guess it shows how much you have to sort of think about how your cache is working, because even with this simple application, then you have all these sort of decision points.
Mm-hmm. Writing cache. Now I run the production run. This is production. This, blah, blah. Stop. I load again. Production log. Cache. Training logs. And now we have 96% of classes loaded from the cache.
Hooray.
So there's still some classes that were not loaded from the cache, but it works much better. Let's make sure that I'm skipping some parts because if not, this will get so long. But we can see that all our interesting classes are here. But they are untrained. Why are they untrained if I have asked for 100 requests? Well, I can check one method. And it says, okay, this method, which is cat photo generator, get cat your image, it doesn't have a method counters. That doesn't mean that it wasn't called. The method counters that have a low number are removed from the cache, because if not, we have lots of things on the cache and it gets really big. But it doesn't have method data, so it hasn't been profiled. It doesn't seem to have been compiled. It doesn't. So this was not a properly done training run. If we do a better training run, it will be this, but with, I don't know, 10,000. Is this started? Yes. You can see here that my laptop is slow. I stop. It shouldn't be, the cache shouldn't be much bigger than before, because then the classes loaded are the same, but now we should have training data. And while this finishes, no, because I need the AOT map file to do this properly. So yes.
This is going to be fun for everybody to figure out. Like they're all, now you're going to find everybody's doing this differently, like doing the training runs and having to add that to their DevOps processes and all that fun stuff.
I load training loads, I load cache. The info should be more or less the same. Oh, because it hasn't loaded yet anything. It's still loading things. Okay. But I can check the describe from before. And now it has a method counters, it has method data, it has been compiled on levels 3 and 4, which are the higher on the compilation scale of things. So now this method is trained. And if you look at the classes, some of them are not trained, which is the beans, because maybe they are not called several times. But my classes from my source code are trained. And I have I have also the warnings, which is the things that were that were shown on the AOT cache while it was being created. And for example, it says, we couldn't add this class because we couldn't find this other class. This is something that we have discussed previously on another channel, that there are some failed verification, blah, blah, blah. So the AOT cache is very strict on what is inside. So if there is something weird, I couldn't find this native, blah, blah, blah on the dependencies, I'm just going to skip it. And that's probably why there is this 4% of classes that are not, I don't have it because I don't have a training run. But this 4% of classes that were not loaded in production run from cache probably comes from this kind of things. You can also say, I'm going to check errors related to this class. You can also search exactly if it doesn't have a, and it shows you which errors are there related to that class. So if you see that something is weird, for example, I see that the cat photo generator is used by this other class, but then something happened weird because it's not trained and it should be trained. So I can try to search for warnings related to any of these classes, which in this case we don't have. So it's something that allows you to explore the AOT cache and understand. The main basic thing you need to check is that all your classes are listed here and they are trained.
Yeah.
If that happens, probably you're doing it right. If that doesn't happen, something is weird. And I could continue using this and show you more stuff, but I guess it's better if we cut it here and then I write some blog post or something.
Yeah, so if people want to try this for themselves, try this tooling, what should they do?
So this is here. It doesn't really have a release yet, but I have a nightly snapshot. You can download this Java jar file and just use it. And I have a very long readme here on how to use this. Why is this class not in my AOT cache? Why is this class in my AOT cache? Blah, blah, blah. But the truth is I don't keep the readme 100% upgraded. So just use the help command. There is a help command here. And then you can say, okay, ls help command. And then it gives you all the arguments. So just explore that and ask me. Please, if someone uses this and finds it helpful or not, I want to know because I'm building this for people to use it. So anyone who wants to use it, please share the feedback with me. I'm looking for feedback.
Perfect. Oh, I think that's probably a good point to stop. But yeah, thank you very much, Maria. Yeah, super interesting. Lots to think about. And as we said at the beginning, I guess there won't be any more episodes of Quarkus Insights until the new year. But we'll be back in the new year, all refreshed and raring to go. And so until then, hopefully everybody can enjoy the break. And we'll see you all in the new year. Cheers all.
Safe and happy holidays, everybody.
Yep.